Our speaker to start our afternoon is Professor Jeff Hare from University of Washington, Department of Computer Science and Engineering, and he got his PhD at Berkeley, was a professor at Stanford for a while, and now has been lured up to UW quite a few years ago, and is responsible for quite a few cool open source graphics and visualization projects. And it turns out, I guess, was the first intern at Tableau back in the day. So thank you.
Cool. Thank you. So good afternoon, everyone.
Oops, sorry. One last thing. If you have a question, whether you're in the room or watching the live feed, tweet it to the @PyData Seattle, and the last 10 minutes, we'll go through those questions, okay? Sorry.
Okay, thanks. So good afternoon, everyone. I'm Jeff Hare, a professor from across the lake here at the University of Washington. I'm very interested in building tools to help people explore and understand data more effectively. So let's just start with a couple examples. So here, kind of in homage to Hans Rosling, who sadly passed away this last year, here's a scatter plot of world health and economic statistics. So here along the x-axis of the scatter plot, we see fertility plotted. Along the y-axis is life expectancy, and then we see countries represented as individual dots. So this really represents a snapshot of the world around 1980. But of course, to understand data more effectively, we don't want to see just static imagery. We like to be able to interact with it, to understand trends, patterns, changes, and so on. So in this particular example, I might want to see something about the individual countries. So mousing over this, I see the label for Bangladesh, but I also see its trajectory. So basically, how has this country moved in terms of its health statistics over time? And I might do that for other countries as well, such here as Egypt or Bolivia. But I don't want to maybe see just the static capture of these time traces. I want to see how everything moves together. So for example, using direct manipulation, I might grab this point and drag it through time. So in this way, I see as Bolivia moves along its timeline, I see how the other countries move in response. And in this case, backwards or forwards, trace out decades of global development. In this case, just using a simple, tabular data set, there are a variety of visualizations we might consider. But of course, as we move into other more complex data types, there's a richer array of visualizations we might use. This is a not very informative visualization showing you all the different direct flights across airports in the United States. And obviously, in this case, plotting all the data simultaneously doesn't lead to a lot of insight. So in addition to plotting tools, we need to have a knowledge as to what's going to make different visualizations more effective. So for example, in this case, I might instead use interactivity to show subsets of the data at a time. So in this case, as I mouse around, I can see the direct flights from individual airports to each other. So in this case, all direct flights from SeaTac to other airports across the US. And as I do this, you might notice that points are selected just as I mouse near them. So we have to worry about not just the quality of visual encodings, but the quality of interaction techniques as well. So for example, if I double click, I will show you the hidden visualization, in this case a Voronoi diagram, that's being used to accelerate mouse capture. So in this case, as soon as I move to a point that it's the closest to my mouse cursor, I automatically select it, thus helping me more easily select different data points within this data set. But I think the real value from interactivity comes really in understanding multi-dimensional patterns. So looking at further data about flights, this is over 500,000 flights from the FAA showing their on-time performance. So this first histogram shows the arrival delay, so how early or late is the flight. The second histogram shows the local departure time, so what was the clock time in the local area when the flight left. And then finally a histogram of distances. And it's useful to look at these just as univariate summaries initially to get an overview of the data. So one thing you might notice is that the mode of this first histogram is actually negative numbers, which is saying basically a bulk of flights arrive early, which may tell you more about the scheduling practices of the airlines than their actual flight times. But nonetheless, having given this overview, we can then explore further to see deeper patterns. So for example, I might take the selection region using a technique called brushing and linking to cross-filter these views. So I move this window around, I automatically not just have a selection, I re-aggregate all the data in the other plots to see how dependent different variables are on the selected view. So for example, I might say, well, what makes flights late? So as I drag out to the right, starting from here, I can see how this distribution shifts. And that as I have later and later flights, they're much more likely to leave later in the day. Now, if you fly a lot like I do, this is probably unsurprising, is that delays can change. So delays early in the day will then propagate, causing flights to be later and later as the day goes on. We can see that reflected here in this data. We might also ask, well, what allows flights to arrive early? And as we shift to the far left and see the earlier and earlier flights, we'll see a change in the underlying distribution of the distance histogram. So for example, we see that longer and longer flights, unsurprisingly perhaps, are more likely to arrive early because they have more distance on which they might be able to make up that extra time and arrive early. In this way, we can explore these things both to get an overview of the data and then to begin to ask questions that might, vary along different dimensions and interactively gain insights into multidimensional behavior, even though in this case we're only using simple one-dimensional plots. So this is one instance of what I mean by interactive data analysis. And so to support these types of interactions, I've been working on visualization tools for a number of years now. So now basically over 15 years of work. And that started with toolkits written in the Java programming language, such as Prefuse, then on through Flash, and then now using web-based systems. So I had the honor of collaborating with my former Stanford student, Mike Bostock, for example, on the ProtoViz and D3 frameworks. And we've since been focusing on the development of higher level languages, declarative languages for visualization such as Vega. And so one problem with all of these tools, if you've done much, for example, in the JavaScript world, is that they might be very powerful, but they're also very verbose. So they might be great for building, very, bespoke visualizations that you might find on the front page of the New York Times, but fairly unhelpful if you want to rapidly build a visualization for exploratory analysis. So one important question we might ask is, how do we author interactive graphics in a way that allows us to build not just static plots, but interactive exploration tools in the midst of analysis? And so one approach that we've been exploring to this is a JavaScript library in a higher level language called Vega Lite. So this is a grammar of interactive graphics. And so by grammar, what we mean is we have a closed system. That is, we have a formal declarative language for specifying things like visual encodings, but also interaction techniques that loop back together. And this is to support very concise and rapid specification of everything from basic statistical graphics, such as histograms, line charts, etc., but also to build multi-view visualizations, like we saw in that earlier flight delay example. That not just taking individual charts and stringing them together separately, but rather having a combined specification that allows us to build multi-view graphics. Whether it's things like a scatter plot matrix, where we look at all pairwise projections of a data set as a set of scatter plots, concatenated and layered views that might allow us to repeat variables to see how they differ, or faceted views where we subdivide the data and then create multiple plots for those different subsets. These are critical parts of creating effective exploratory graphics. And then we want to add to these interaction. So as a first-class citizen of these visualizations, you'd be able to do not just selections and panning and zooming, those are of course very important, but also specify transformations of the data interactively, whether it's re-indexing data, such as in the stock chart, panning and zooming to also create filtered views, and then also cross-filtering below, as which we saw earlier. So this way we want to be able to support not just these static plots again, but really rapidly create interactive graphics. And so fortunately, we've had some support in doing this, so we're very honored to partner with Jake Vanderplas and Brian Granger in creating Altair, which is a Python library for using the Vega Lite language. And while I would love to give a keynote just on all the intricacies of Vega Lite and Altair, many of others have already done this. So for example, my students gave a talk at OpenVisConf, so if you want to know more about interactive specification using a declarative grammar, please see that talk. If you'd like to learn more about some of the motivation from Altair, you can say, just rewind 1 year to Brian Granger's talk here at PyData around Altair. And so while these things are great and you're excited, I actually want to spend my keynote focusing on a slightly different question. Rather than getting into the nuts and bolts of how to build a visualization, let's pop the stack and ask our question, how might our tools help us become better analysts? So that is, getting beyond the nuts and bolts of these tools and how they work, how do they function within the larger process of making sense of data? And so one question that unfortunately all too often goes unasked when we talk about visualization is not how you build that, but rather, should I even build that visualization in the first place? How do I gauge which visualization is effective or not? So a starting point for our tour today will be then to ask the question, well, what makes a visualization good? Let's start thinking about that and use that as a foundation from which to think about how we might start building more powerful data tools. So to start to answer this question and give you a sense of some of the research in this space, let's just do a quick experiment. I'm going to show you two shapes. Your job is to just make a value judgment. How much larger is the big shape compared to the small shape? Don't cheat by using your thumb or a pencil to measure. Just make a quick visual estimate and keep it to yourself, and we'll take a quick poll. So first off, here's two circles. Make a quick estimate. How much larger is the big circle relative to that smaller circle? Or in other words, how much would you have to magnify the area of the small circle to arrive at the larger circle? So raise your hands if you think the big circle is 4 times larger. All right, and as you do this, look around the room. Okay, 5 times larger. Some more, 6. All right, 7, 8, 9, 10, 11 or higher. Okay, so what's wrong with your guys' eyes? That was a very long-tailed distribution. We had everything from 4 to 11 plus with the, so basically we were talking about a lot of entropy here, right? Not a lot of consensus. Now let's look at a different example. Here are 2 bars. Do the same exercise. How much larger is the big bar relative to the small bar? So go ahead and make your visual estimate, and we'll take another poll. How many people think the large bar is 4 times bigger? No one. Okay, 5 times? Okay, I don't see me. No one. 6? Okay, 7. All right, 8? 9? Whoa, big drop off. 10? 11 or higher? Anyone? You voted twice almost. Yeah. Okay, so obviously already, a much tighter distribution. You might have everyone clustered around 6, 7, and 8, as opposed to being spread out between 4 and 11.5. So in case you're wondering, the answer is the same in both cases. It's 7. So here's a way. Obviously, you'd have to melt these circles down to accurately fill the circle. That's 7 here, 7 there. So why is it so much easier in one case versus the other? Well, there's actually nonlinearities in human visual processing. So there's an entire research area of graphical perception dedicated to try to study these differences and what we actually visually decode from information graphics. So for example, here is the results of studies we ran using experiments deployed on Mechanical Turk, looking at estimation error for a variety of different graphics. So we have bar charts with basically different bars, either stacked or with distances between them in terms of position and length. Also looking at angle, circular area, rectangular area. And you see this fall off. And these are showing 95% confidence intervals of the error. And so by looking at these results, we can actually gain guidelines for more effective visualization design. So in this case, if I want to support the task of quantitative comparison, so basically proportional judgments, I will prefer position encodings to area encodings, as we all just experienced. And so we can turn this into sort of rankings that can be useful for design. So for example, given that task of comparing proportions, I can consult these types of resources, or even create algorithms that use this as a resource for making informed decisions about which charts might be better to show in a given situation. So for example, here's a type of map that you might see all too often. This is called a choropleth map. That means it uses color as the encoding of a state region, in this case using a geographic projection, to communicate some quantity. So in this case, it's data about political donations and how many were made in different states. So in this case, you can see Texas and California might have given more, which probably isn't surprising because they have a greater population. But other things might be quite difficult to see. So not only is color a less effective encoding channel, as we will see from those rankings, we also have confounds with shape. Also sometimes confounds with projectors that make things even more difficult to see. So things like what happened in Delaware or DC or Rhode Island might be much more difficult to see due to relative sizes. So for example, we can consult these kinds of resources and say, well, instead of using color hue, what other visual channels might I like to consider? Well, X and Y are already taken if we want to keep with a map. So maybe we'll instead walk up and use something like area, such as the size of a symbol, to communicate the quantity instead. So in that case, we'd go from this color map to one using size symbols. So in this case, these dark filled circles basically show the quantities that were shown in the prior display. So in this case, you can see, yes, California and Texas do have higher values, as we saw, but DC actually has a huge number of contributions that was invisible in the previous map. In addition, we actually get some more latitude for interaction. So I told you the filled circles show the data I showed in the previous map. In this case, those empty circles show totals. So those dark circles are actually just showing a subset, and we actually now see set-subset relationships by having symbols within symbols. So not only did we gain some more perceptual clarity, we actually gained more degrees of freedom with respect to showing interactive selections and how they compare in different states. So what to visualize, again, is more important question overall than what tool you use to show it. Just to round this point home, I want to share with you my favorite example of a perceptual redesign. This was done by Michelle Borkin and colleagues while she was a PhD student at Harvard. And they worked in collaboration with doctors at Massachusetts General Hospital to try and explore different visualizations of arterial stress. So in the bottom left here, you saw was actually the state-of-the-art display at the time they started their research. So this is an anatomically correct 3D model of an arterial tract, and then colored using a default rainbow color palette to show you your shear. This is something a doctor would look at to make diagnostic decisions, for example, whether to administer certain blood-thinning drugs, or in an extreme case, as part of the evidence that would go into making an operation decision. And you can see in these other quadrants here alternative visualizations. So in one case, moving from a 3D model to a 2D model, where in this case you instead represent an artery by cutting it open and unrolling it, and then ditching anatomic exactness to instead show sort of topological connections between arterial tracts. The other design move here, of course, is changing the color scheme. So for example, going from a rainbow color palette to a more perceptually motivated diverging palette that diverges into red for the areas that are going to be most troublesome or most worrisome to a doctor. Now the real interesting examples here though is what they did when they evaluated it. So they actually put this in front of real doctors with real diagnostic tasks to see their accuracy with these different visual encodings. And actually quite shockingly to me, here's the results, each of which were statistically significant. So you have with a state-of-the-art visualization at the time, roughly 40% diagnostic accuracy. Simply changing the color scheme moved 30% up. So you have like 71% accuracy in this bottom right. And then moving from a 3D display to a 2D display gave you an initial roughly 20% boost, almost as an independent factor in improving people's ability to spot trouble areas and make appropriate diagnoses with these visualizations. So these different choices of visual encoding really do change what we see, how easy we see it, and how we make valid comparisons. And so knowing something about what makes a visualization effective, is really important, because I think most of you would have, not have a hard time deciding which of these displays they would prefer that their doctor use. Right? So these are not just a matter of intellectual interest. They have real-world consequences for what we do and don't see in data. So we can use this as a basis to start to figure out how our tools might make us slightly better analysts. So one might be by providing some smarts in terms of appropriate visual encodings. Well, now let's look at a slightly broader question, given that foundation, and say, well, how might we support more effective data exploration overall? So given a new data set that we're trying to get familiar with, we might have some hypotheses to begin with, but others that might be nascent or discovered as we start to interact with the data. How do we really make that process more effective overall? Well, it's a hard question to answer, but one where I think tools can play a role. So just as one example, here's a data set taken from a juvenile corrections department from the state of Maryland, actually from a couple decades ago. The most important thing to know is that this is about juvenile criminal offenders who've been processed by the system. And the other most important thing to know is that the x-axis is age. Right, so as the father of 2 young children, I can tell you I am very concerned about the rise in violent infants. So there's clearly, something, maybe it's just the state of Maryland, maybe the West Coast is different, I don't know. But as the son of a wonderful 95-year-old grandfather too, I'm also very worried about these marauding centenarians out here. So as you may have guessed, what are these? These are actually, data quality issues. In these cases, when the age of some juvenile was unknown, different administrators had different policies of dealing with the fact that the integrity constraints on the database did not allow them to enter unknown as an option. So either opted for 0, the minimum, or the maximum value allowed by their interface. Now, and that explains a lot of this data. Unfortunately, I have no good explanation for you why a 35-year-old is in the middle of this. I don't know, maybe they were particularly baby-faced. I can't say for certain. Nevertheless, data quality issues are one thing that obviously undermine exploratory analysis and something our tools can do a lot to help us identify. But I think a deeper and pernicious problem is what we might refer to as blinder vision. So after years of teaching visualization and data science classes, a recurring trend I see is I give people an exploratory analysis project. They pick an interesting data set, they have their candidate hypotheses ready to go, and then they deep dive right into the data, often jumping into multivariate views without ever assessing simple univariate summaries, without asking what-if questions about what are the ways the data collection may have been an error. Or they might even overlook latent factors that are actually more explanatory because they were so focused on their pet hypothesis. And so thinking about how to make exploratory analysis appropriately broad or comprehensive is another interesting thing to consider. And so there are many pitfalls in analysis. I'm sure if we brainstormed in this room, we could come up with a very long list. So I shared just 2, right? Overlooking data quality issues, fixating on specific relationships. And of course, we know from both the intelligence analysis and the psychology literature that we as sort of limited human beings with constrained cognitive capacities have many other types of biases that affect what we see and how we think about things. So maybe our tools can play a little bit of a role in nudging us, away towards some of these more unfortunate tendencies. And so that's actually one thing that we're starting to explore in projects such as Voyager, which is the idea that support, rapid interactive analysis of using visualization, but to do so in a way that also supports you being a bit more broad in your consideration and helps you not overlook certain data quality issues. So let me just go ahead and jump into a demo of this tool. So here's the Voyager 2 UI. For those of you familiar with tools like Tableau, you might notice some similar elements. We have, in this case, a data set about cars. This is automobiles over a number of years. Different data fields with different types. So we have string data, numerical data, et cetera, laid out here with our schema. And we have visual encoding channels. So if we wanted to, we can drag and drop a variable and make it the x-axis, the y-axis, a color encoding, et cetera. All of these, which under the hood are actually being transformed into Vega Lite visualizations. So this UI is actually just a way of specifying formal statements in the underlying Vega Lite language. But probably what drew your eye first is this gallery of visualizations on the right. In this part, all we've done is loaded the data set. We actually haven't specified a visualization, but we've automatically populated a gallery of recommended views. So this includes, basically summary views for each variable within the data set so that we can get a quick overview of the shape and structure of the data. So this includes, histograms of all of our discrete measures, and then onto our, quantitative measures. So in this case, we can see, some have normal distributions, others look perhaps more log normal in nature. And doing so, we hopefully can spot any, unexpected values or outliers that might underlie subsequent analysis. So looking at this, I also noticed that mileage or miles per gallon, is one of the properties in the data set. So if I'm interested in that, I might start build up views on my own. So for example, I might grab miles per gallon, drag it to the X field. Here I get a horizontally oriented dot plot. I can, change the axis if I wanted to log scale it. I could also just transpose the view. Now I have it along the y-axis. And you'll notice that while I've specified a specific focus view, I'm still getting these recommendations, but in this case, they're based on the view I'm currently looking at. So it's actually taking the Vega Lite specification for this view and then automatically identifying ways to generalize that and then present related visualizations. So I might see summary views such as a histogram or the global average, which in this case is about 23.5 miles per gallon. And I also see what happens when I start adding fields, basically in a search frontier. What happens if I look one step forward in my analysis, but do so in a comprehensive way so I don't overlook potential relationships of interest? So for example, here I see that displacement, horsepower, and weight all follow very similar curves. They look rather quadratic in nature, but the relationship between acceleration and miles per gallon is quite different. So if I want a car that's fast but also has good mileage, that was built somewhere in this case between the 70s and 80s, it's an old data set, I can see that at the time, the top cars for those criteria were Volkswagens. So here's a VW pickup, here's a Dasher, and so on. And so I can see these outliers that may be of interest if I'm looking for a fast but fuel-efficient car. As I scroll down, I can see other relationships automatically as well, right? I can see that as the number of cylinders increases, mileage tends to decrease. I can see that, as I can look at different origins, and it seems like the USA seems to be creating the least fuel-efficient cars, which, we should say, is that true, or is there latent factors? That's something we'll come back to shortly. And then finally, I see, this plotted by time. So I can see that mileage appears to be improving over the years included in this data set. So let's say I wanted to learn more about that. If I mouse over this icon in the upper right, I actually automatically fill in the specification view what would be necessary to build this chart myself. So you actually scaffold learning by you seeing examples. You can quickly see how to build it yourself by looking at this preview. I go ahead and click this. I'll make this the new focus view, and then I get recommendations that are then conditioned on this being my focus chart. Here I see raw data, but perhaps I'm interested in looking at aggregates instead. So this is actually the average mileage plotted here. So maybe I'll switch to this view instead. And then I see some breakdown by some different categorical fields, so including the number of cylinders, and then getting back to something we just saw a few slides ago, different origins. And indeed, it looks like the USA is doing poorly in terms of mileage relative to the Europe and Japanese markets across time. So let's look at that more closely as well. And as we go to this other view, we see we get alternative visualizations. So for example, here I have a line plot with layers, but if I had lots of series, maybe it makes more sense to break them off in a faceted view. So you see I have alternative codings recommended here, such as seeing Europe, Japan, and USA individually. I can also choose to filter the types of recommendations I get. So for example, showing me only things where we add new categorical fields to the display. In doing so, we see a plot here that has the cylinders broken up into facets and then includes origin as color. And we see that while indeed the USA does poorly overall, it's also the only region producing 8-cylinder cars, which is sort of by their nature have worse mileage. So a more fair comparison, if we're interested in comparing these different markets, would be to look at the 4- and 6-cylinder cars, where we might get a slightly more fair comparisons and not be subject to ignoring latent factors. So in this way, we want to explore topics of interest, but also be exposed to the breadth of the data. And this is what the Voyager tool is trying to help accomplish. So going back to the slide deck, We ran a study of this and we tried to see how people actually change their data exploration patterns using a tool like this versus a UI modeled after Tableau. And what we found was that compared to these existing tools, Voyager led to over 4 times more variable sets seen. So people are seeing a much broader swath of different multivariate combinations of their data. And they're interacting with over 2 times more of this. So it's not just a thing that these are being rendered on the screen and ignored. People are actually engaging with at least twice as many different plots with unique data variables driving them. Looking at some of the qualitative feedback, people said something like, the related view suggestion accelerates exploration a lot. So people found this really sped up their ability to get a comprehensive overview of a data set. It also aided learning, as people said, I like that it shows me what fields to include in order to see a specific graph. Otherwise, I have to do a lot of trial and error and can't express what I wanted to see. But we also saw that maybe these things can, in certain instances, work maybe too well, in the sense that, one person said, these related views are so good, but it's also spoiling that I start thinking less. I'm not sure if that's really a good thing. So I think this is really interesting, given the scale of data, both not just the number of records, but the number of variables, human cognitive biases, some amount of automation can be really helpful. But there's clearly a delicate balance that if we go whole hog and automating data analysis, we're going to throw out the baby with the bathwater. And we also run the risk of people becoming passive receptacles of what some pre-configured set of algorithms say, rather than driving the analysis themselves. So really having this right balance between the analyst and computation within these interactive sessions, I think, is critical. And we're looking forward to exploring this more. We're further refining the system. I'm also excited to share that we're working with Brian Granger and others to try and bring this as an integrated component within the nascent Jupyter lab environment as we bring both Altair and Voyager, these things that we've been developing largely in the JavaScript ecosystem, but hopefully making them valuable in the Python data science world as well. And so we're really excited to be working on that, very thankful for the collaborations that we have there. But of course, all the examples I've shown so far have really focused on visualization. And that's not surprising given how passionate I am, but also how highly developed our visual senses are. It's really a high bandwidth communication channel. Nevertheless, visualization is, of course, just one component in the much larger process of data analysis, including how we acquire data, clean it up, integrate diverse data sets, build models, and then also getting into social functions, like how do we share our results, get feedback, disseminate things more broadly. It would be lovely and ideal if we just, moved from one step to another in sort of an uninterrupted flow. But of course, that is a fantasy, and the real world looks something much more like this. As I'm sure you've all experienced, for example, visualization is often the front line of defense against incomplete or bad data. So I might visualize something and realize I might have to acquire new data sets, engage in additional cleaning. There's all these feedback loops that make the heart of this interactive process, that even if we have automated machine learning algorithms, we're spending an immense amount of time, in human-driven feature engineering, model validation, and looping, et cetera. So understanding the interactive nature of actual data science practice is critical to identifying some of the pitfalls and making our tools better. So to understand this a bit more broadly, my students, collaborators, and I also conducted a number of interview studies. So here's one quote that we really like to share. This came from a study we did back in 2012, where data scientists in industry said, I spend more than half of my time integrating, cleansing, and transforming data without doing any actual analysis. Most of the time, I'm lucky if I get to do any analysis at all. And so I've shown this quote a lot, and every time I do, I get a lot of pushback. People are like, this quote is just not right. Did anyone guess why that might be?
80%.
Yeah, exactly. So this gentleman yelled out 80%. So everyone has showed this like half. This is the luckiest data scientist I ever met, that they only spend half their time cleaning up the data. And so, it's like, that maybe, at the time when we first were unearthing this, we're surprised this wasn't, a bigger issue in terms of tooling around data wrangling, preparation, integration, et cetera. So at the time, we felt it something like the elephant in the room of data science research. Since then, I think this topic has gotten a lot more attention, both to our efforts and many others, is basically as practicing data science became more popular and more well-known, you just couldn't ignore the magnitude of these issues. So that nowadays, we instead have things like big data Borat opining. In data science, 80% of time spent prepare data, 20% of time spent complain about need for prepare data. Right, so obviously, there's a lot of interaction happening with data even prior to building models or creating, informative visualizations. And so, that leads to other questions that we might try and ask in the realm of interactive analysis. Like, how might we support interactive data wrangling? And this is something I've been working on now, for over a half decade. I'll show you sort of like kind of a now classic result students and I worked on back in 2011. But before I do, I want to show you, like, this isn't just nasty data in the form of missing values or like horrendously designed log files that you then have to map back into a table, something I like to call should be structured data. It's in some weird text structure, but it really had no need to be in that weird idiosyncratic format. Even sort of well-curated data often has these issues. So for example, here's the US taxpayer dollars at work. This is data you could download from the Bureau of Justice showing housing crime statistics. And this is designed for human consumption, really in a spreadsheet environment and nothing else. So it's well curated, but you can load it into Excel. But if you try and load this into pandas or into R data frames or into a relational database, it'll break upon import because it's just not formatted appropriately. And so to explore some of these issues, we built a set of interactive tools for doing data preparation. And one of the early research systems we built was one called Data Wrangler, and so I'll share a quick demo of that now. So here's the Data Wrangler UI using the same data set we saw in the previous slide of housing crime data. It's broken up by different states, and each sort of has its own submatrix. We've loaded it into a tool, and we see a somewhat familiar spreadsheet style UI. We see a couple operations have already been performed that we recognize some delimiters, so we split the data into rows and columns, in this case based on tabs. And I could go on and imagine I had a set of commands I could evoke from a menu. That might be one way to try and clean up this data. But we again wanted to support interactive transformation. We initially played with a gesture language, but we found our gestures rapidly end up being ambiguous. Like the same movement that someone demonstrates might mean different things based on context. So this actually took us down more of an automated recommendation and machine learning approach. So now I indicate what I'm interested in, such as in this case, I'm interested in row 2. Well, what might I do with the fact that I selected that row? Well, one inference is to just delete that row. But I can also examine the contents. I see that row is empty. So the second suggestion here is to delete all empty rows. And doing that, you see I get a visualization which then highlights what the change to the table will be if I choose that particular recommendation. So it turns out visualizing the effect of a transform was a key part for having people make sense of this tool. So in this case, it does what I want. So I go ahead and hit enter. And now those rows have been removed, and I can go on with cleaning up this data. My column headers are actually buried within the data, so I'd like to extract out that metadata. So I click that row, and I get some different options, including the ability to promote it to a header row. So I can go ahead and do that. But of course, that was repeated, so I want to get rid of these additional header rows, so I can do that. Here, one suggestion is to delete these rows based on exact value matching, and that works in this case, so I go ahead. And now I'd arrive, which might be kind of the more complex operation in this chain, which is extracting the state names to make them part of the data. Currently, they're kind of buried within this text label. So to indicate my interest in that, I'll just go ahead and select the text Alabama. And the system infers I'm trying to do an extraction procedure. And indeed I am, but the initial inferences are fairly simple. It's, in this case, matching by position within the string or by exact content matching. And I can immediately see in the preview that this doesn't work. For example, Alaska is not selected, Arkansas is cut off. So rather than waste my time with the suggestions, I can go ahead and just start giving it more examples so that I can better generalize its inference. And now I see that this looks good on this column, and the top suggestion is to extract from the column year after the text in, which also looks very appropriate for this data set. So I can go ahead and hit enter, and underneath the hood we've actually learned a regular expression pattern for performing this extraction. Now as I'm doing this, you may have noticed some other features of the display. For example, this little numerical icon indicates that I've inferred that this is largely numbers. And here in red, I can actually select all the things that fail to parse as numbers. So I'm starting to get some initial type safety and data quality feedback. Meanwhile, over here in gray is showing me the proportion of cells that have missing or empty values. And so if I wanted to get suggestions of what I can do at a column level, I can go ahead and just click the header, and I get some suggestions which include interpolation or filling. So in this case, it's actually filling down the empty cells based on the observed values. So in this case, I can go ahead and do that now. I've filled out these cells with the state name, and I want to get rid of these rows I no longer need. For example, let's say reported crime in Alabama. And, I could just throw away things that don't parse as numbers, but that could be brittle. And many spreadsheets actually have a value plus an annotation, which might break type inference, but might actually be something I want to keep. So to be a bit more specific, I'll say I want to get rid of the rows that have the text reported crime in. The system initially infers I'm doing an extraction based on a text selection, but I can also give it a hint that I'm interested in deletions, and that helps limit the number of different transformations it might consider. And then here I get, as my top suggestion, delete all the rows with the text reported crime in at the beginning. This is indeed what I want. I have a nice query, so I can go ahead and execute it. And now I have a relational data table I could actually load into any kind of standard analysis tool, sparing you the minor detail of just renaming that column. So at this point, I might go ahead and click Export. And because this data set was relatively small, it fits in memory in this browser-based application, I can just automatically emit all of the data, in this case in CSV or TSV or JSON, pick your data format. But as I've done this, what we've actually learned is a script, right? So this history down here is actually just a rendering of underlying programming language statements that we learned through direct manipulation interaction. So I could use this to actually cross-compile to different languages. So in this initial research prototype, we actually, for example, generated Python code that would then run within a quick and dirty Python runtime we implemented as a proof of concept. We've since taken this research along further and now do things like generate scripts that will run at scale, doing Hadoop jobs on Spark, for example. So I can actually interactively demonstrate a transformation script, get feedback, and then turn that into a program that I can then execute to run, at scale. So that was the idea, behind things like the Data Wrangler project. And so since then, we've commercialized this. We started a company called Trifacta, which releases a free tool that you can download if you like called Wrangler that supports a number of these similar operations. In this case, you're seeing a data table of contributions to political campaigns in the 2016 election cycle. In addition to the table, you see histograms. So we have like preview visualizations to aid with data quality assessment throughout the way. As I demonstrated before, interactions like selecting text will lead to visual previews of possible transformations. But in addition, we've been exploring ways of doing automated visualization. So for example, if I come here and instead say, hey, given these candidate names, give me a profile of this particular column of my data set. And so it'll tell me things, like statistical summaries of different properties of the data, of type issues, of outliers, et cetera. And in this case, for string data, to understand what's an outlier, we actually look at the length of the strings, which is a simple but strangely effective heuristic for actually spotting untoward values in your data set. So if I want to, I can actually interact directly with this visualization. So on this box plot below, I can actually select the bar corresponding to the outliers that are high and get transformations relative to those, including filtering them out or isolating them for further analysis. So for example, if I elect to keep only the outlying string values representing candidate names, I then get this data table subset, which, getting away from sort of the political morass of today, we can look at what are some of the candidates you've never heard of who didn't make it. These are all people who actually have legitimate financial transactions behind their name. That includes candidates that is basically the letter A with caps lock stuck, pressed repeatedly. That is, what else do we have in here? Lindsay Lohan, Emperor Goku. I don't know who that is. Remo, the cutest dog ever, the mini schnauzer from the dog party. Who else? Oh, Alexander Soy Sauce and Taters, Master First Gourd from the nap party. So there's this whole strange world of fringe candidates that had you just been dealing with this data, through symbolic tools, you probably wouldn't have known exist. This could have actually, maybe, biased your analysis in certain ways, in ways that you might prefer to remove this data. Or if you're, maybe a journalist, maybe there's a whole interesting story to be told in investigating what's going on these strange fringe candidates who are actually registered with the Federal Elections Commission. So in this way, interaction can also make us aware of some of the things that we might have overlooked. And so this balance between human-driven exploration and automation, again, proves quite interesting. So more generally, I want to say that contrast sort of a typical approach to data analysis. So it might involve things like you start with a data set, you start writing scripts for transformation and visualization. If it's very large, you might also have to then extract a sample of that data to work with. You then run your scripts on that data, and then you might visualize the output. So you might, like whip up matplotlib and create plots based on the output of having already run this transformation script, and you might, iterate, et cetera, until you finally arrive at a suitable set of analysis procedures. And what we're exploring across these projects, both the Voyager and in the Wrangler projects, is a way to actually meaningfully invert this process. Actually start with visual representations of the data, whether that's text tables, summary visualizations, et cetera, and enable interactions with those, and then use that as evidence to see the search process. So underneath the hood, in both cases, we actually have a language model, whether it's languages for representing visualization or languages for representing data transformations. And then we actually do search and ranking. So we use enumeration and machine learning procedures to try and identify what we think good responses are to what the user has indicated they're interested in. And then closing that loop through visual feedback, whether that's new visualizations or visual previews of what transformations would do, to then kind of create a technique that's hopefully faster for experts, but also much more accessible for people who know their data but aren't necessarily programming wizards. And so that's the types of things we're trying to explore in supporting interactive analysis. And so to wrap up, I'd like to share just some parting thoughts as we begin to explore this sort of space of tools. And I know many of you are avid data scientists, and many of you are probably also data tool builders. Some of these things might be things that you consider as you figure out building tools that people beyond yourself will be using to conduct analysis. And so what are some of the considerations that we've come across in this short talk today? Well, one is a careful balance of automation and control. So by using automatic recommendations or machine learning, we're going to be able to expedite and also make broader the process of analysis. But to do so, we want to maintain the control of the analysis, the analyst, at the center of this process. For example, there's many pitfalls to automation, as I'm sure you're aware. That's like loss of agency, intuition, and domain expertise. We want people's understanding of the domain, which vastly typically outstrips just the data resources you have at hand, at helping guiding where the analysis should go, what things are genuinely surprising versus what are just noise. All these things often require human judgment. And if we just black box too much of this and automate it, we also run the risk of putting poor models loose in the wild, which could have devastating consequences for various organizations, from government to industry, and certainly in health as well. But of course, we as humans have limitations too. We have our cognitive biases, we have blinder vision, and we make mistakes. So what are the ways in which these tools can actually help offset those? By having a better understanding of human capabilities, whether it's what makes a visualization effective, or what are common errors that people encounter in their reasoning or exploration of data, and trying to think about the design of tools in ways that help counteract them is, I think, a critical concern. And so to do that, what we'd explored in these projects was enhancing interfaces with underlying models of capabilities. So what do I mean by models of capabilities? Well, in this case, it was twofold. Like, to really enable these applications, we had to look at the language level, again, visualization or data transformation languages, that gave us a base to formally reason about the steps a user might take. Then we think about, within those types of steps, how can we rank them or recommend them effectively, whether it's using visual perception guidelines that help us pick more effective visualizations, or knowing based on the the data types and relationships what transformations seem most needed at the time. And as we build these things, these models that we build to help power these applications themselves are going to require curation. And so I think an interesting problem that we're all going to face going forward is how our interfaces themselves are going to learn from us over time. And I think data science is a particularly rich petri dish to explore these issues that I think will have much larger resonance across many areas of software. So how are these interfaces going to learn, and how are we going to help shape them in the most appropriate way that the models they learn really do help a larger swath of people get their job done effectively? And so along the way, I think there's going to be a lot of interesting meta challenges as well. So it's going to require the means to inspect, monitor, and audit the models that are underlying increasing number of the interactive sessions that we experience today. And so I think the type of tools and expertise that are being explored by a community are going to be critical to these issues going forward. And so be very happy to engage you all in conversation afterwards on any of the topics that may have resonated with you. And so with that, I'd like to wrap up. I also want to thank all of my collaborators and students over the years. Here's just a small sampling of them, along with different funding agencies. I'd also like to thank you all in this room. My group, myself, my students have made immense progress building on a number of the open source tools that the Python community has developed. So thank you for all that you produce and all the examples you provide. Thanks.
Thank you, Jeff. So we have actually quite a bit of time for Q&A here, about 15 minutes. So I'm just going to take a few of the questions from the feed. And if you have other questions, by all means, at PyData Seattle. So one question that came in was, you showed a chart, for example, of what was effective in terms of human perception and like color, which is probably the most widely used differentiator for categorical variables or something. Was it actually at the bottom?
Oh, that's a great question.
And are there other places, other resources we can go for guidance on those sorts of issues?
Yeah, let me pull up another slide to help add some more nuance to this. Okay, so this is from, It was a hidden slide, so I didn't want to show. So here's actually a ranking. So the critical bit to that question was, what about the use of color? Well, keep in mind this is specific to a task. So in this case, the task was comparing quantitative data. So if I'm seeing two values, I want to say how much larger is one value versus the other. That is a task for which color is actually fairly poorly suited. So if I wanted to make precise estimates, is this 5 times or 10 times larger? Color is a very poor channel. If I want to make order judgments, which are different, without worrying about magnitude, is this greater than or less than? Color is actually much more effective in that than it is for proportions. Whereas for categorical data, if all I care about is this equal or not equal, I'm going to make basically a category judgment. Color, you'll notice here, color hue is the second most effective here. Now that's contingent on the fact that you have a small number of categories. Particularly once you go over 20, color breaks down very rapidly because you lose color discrimination. So, an important nuance to add here is that the effectiveness is not just relative to the visual encoding channel, it's relative to the type of comparison task that you're making. And so what you're seeing here, this list was actually used by Jock McKinley, who's now at Tableau. He did a thesis back in 1986, was one of the first to take perception data and then apply it to algorithms for automatically ranking and suggesting visualization designs. And so basically, based on the data type, which is a proxy for the types of comparisons you want to make, you can actually choose which of these rankings might be most effective to apply.
Great. And so actually, just for my own edification, there's McKay, and then there's also the Cleveland and McKay.
Yeah, so Cleveland and McGill was worked on, so they were, Cleveland is a famous statistician who actually did work in applied psychology, did work on graphical perception. McKinley picked up that work and others to actually bring that into computer science to build automated systems that leverage some of that knowledge.
Oh, okay. So another question is, you mentioned a couple of times, including in your wrap-up, about sort of tunnel vision that people get, and I mean, I've run into this myself as a data scientist, right? You're working with some domain expert, and they say, well, customers always buy skis in some month, right? Mm-hmm. And that maybe is their perception, and they're so fixated on a certain thing. Do you have tricks or tips for sort of expanding that view when you're doing exploratory data analysis?
Well, I think the people I've met who are most skilled at analysis already have some of this skepticism baked in. I think at the end of the day, it's just like imparting, and especially if we're teaching courses, imparting heavy doses of skepticism around data is something I do continually throughout a quarter. Skepticism, asking questions about how this data was collected, who collected it, for what purpose, what errors are likely to arise. And if you're very certain of something, that's fine. Go ahead and visualize it to actually, a lot of exploration is not just, did I discover something new? It's like, did I verify that my assumptions actually hold? And that's everything, from like modeling assumptions, are data distributed in a way that the models I apply will actually have the appropriate distributional assumptions, to are there, strange outliers that I didn't expect? All of those things, you have to be skeptical and open to surprise. So you have to teach that, and as I showed today, I think some of our tools could do more to accelerate that process, making it easy to generate, a larger set of views to make those types of judgments.
Maybe we get a new one. So one question is, when you're looking for, say, you talked about, which is something a lot of people do in practice, use visualization to check data quality and look for outliers. But like I even noticed in your automotive example, like there was what looked like outliers, but then when you showed the brands of the cars, it was clear they were like luxury cars that didn't care about fuel economy, I suppose, because their buyers probably weren't sensitive to the price of their fuel. So are there ways you can, it seems like a tension there between what's a real mistake.
Yeah. Well, I mean, an outlier is just
something that's
a kind of a statistical term, and how you define it can vary based on different thresholds you set. Interpretation is up to you, right?
Right.
So is that outlier an error, or is that an interesting finding? Maybe I didn't think to include that category. Maybe it'll tell you something about how you want to collect and categorize your data, so that actually becomes a factor in a subsequent analysis. So what you've demonstrated, that's the whole point of doing interactive analysis, is to become aware of those things, and so that you can take appropriate steps to deal with them.
Great. And let's see. Let's see if we got any more here. So what about, so everything you showed was projected, and in almost all computer graphics are projected onto a 2D surface.
Yeah.
But they've been experiments going way back into the 70s, I think, with spinning scatter plots and 3D plots and more recently a few things with like virtual reality headsets.
Yeah.
Do you see a role for that beyond?
I think
it's just adding complexity for no reason?
I mean, even back in the the 90s, for example, a number of my colleagues in scientific visualization explored caves. They'd even this immersive environment.
Oh, right.
They're mostly dealing with like physical data, where you usually have 3 spatial dimensions in time. I think those things are interesting and worthy of further exploration. I also, I intentionally don't prioritize those in my own work for a number of reasons. So some of the things that you talked about with like rotating scatter plots, you can do that with a 2D projection. You can do all kinds of multi-dimensional projections and do rotations and still get some instance of structure there. More generally though, 3D suffers from a number of issues. So one is occlusion, so things can block them, which means you actually have to do things over time. It can't just be your eyes moving around. You have to rotate things or have them rotate and understand the structure. There's also great limitations to depth perception. So if things are visualized, let alone like real world depth perception, not even just like on a screen, which is even worse. So for example, you'll have much poorer inferences relative to that. And also it's found that like rotational judgments are actually demand more cognitively. So you're actually maybe privileging people who have higher spatial reasoning ability than you would otherwise. So in almost all cases where I've seen, a 3D visualization might be valuable as an overview. Like if you're used to, for example, like I do this with brain scientists, you see a view of the brain, you're used to thinking of it as a 3D object. The useful visualizations are almost always 2D slices, and the 3D view is used as an orienting and navigation device. Okay. So in almost any time you can come up with a design that gets the information you need more directly visual in a 2D display, almost all studies I've seen in those cases show improvements. That's not to say you shouldn't use 3D at all, or that there might be interesting applications, certainly in education or immersion for like virtual reality or augmented reality experiences. I would just impart a healthy dose of skepticism, because putting simulator sickness aside, there are fundamental perceptual things where like 3D maybe doesn't perform as well as we might otherwise like.
Right. I've even noticed that with just 3D surface plots. It depends on where you put the eye. You can get a totally different idea of what's going on. So, we noticed in your, when you were showing like the data cleaning tool, do you think it would help to have some visualizations alongside that, or does the screen, like the cleaning tool you showed, which was very cool, so you kind of see, I don't know, histograms change, or maybe you can't even get to that point till you do.
Yeah, well, there's some issues there. Yeah, so when you have like, if you know nothing about the structure of the data and you end up with just a raw text blob, well, at least you can do is actually you can build out character histograms or bigram histograms. Like, they may not be super useful, but certainly as I showed with the Wrangler tool that we released from Trifacta, like every column, once we know the data type, we have some sort of summary histogram. You can dive down. What I didn't show is things like you dive down into a geographic data, the profile will include maps. If you drive down into time series data, it will show you different things like basically by weekday, by month, as well as by chronological time. There's a lot of automated visualizations you can give people based on the data type and some statistics of the data that can really rapidly accelerate that data cleaning process, so that you can just see the things as opposed to think that you have to build them, spend the time to build the chart, then view it, then repeat. So there's a huge amount of effort that you kind of erase with some appropriate design that's very task specific. The thing I would add though is that like we saw, the Voyager tool, for example, was designed for exploratory analysis. And when your data is relatively clean and you really want to start exploring relationships and hypotheses, you have a very different set of task constraints than when you're focusing on the early stage of just cleaning up the data and getting it prepared. And like the understandings that will emerge can overlap, but I think understanding, kind of the specifics of those tasks can lead to tools that kind of, for lack of a better word, kind of better cognitive ergonomics to help people get the job done effectively.
Yeah, cool. So one surprising result you showed was the one with the arterial visualization, that in fact the more abstracted view was more accurately or more interpreted by the physicians than the one that was meant to look more physiologically correct.
Yeah.
What do you think contributes to that sort of perceptive?
I think in that case, among other things, the physiology did not, certainly the 3D running had little bearing on effectiveness for the task. So it was basically, I think in that case, my hypothesis would be that was superfluous information, that if anything just distracted from people identifying the patterns that mattered most. I think occlusion mattered too, like the fact that they unrolled the arteries into a flat display so you can see the entire surface mattered. But nevertheless, I was actually very shocked by that study, because I would have thought maybe the 3D as a result of occlusion would have had a bigger effect. But it was actually the change in color. And that because by making those darker reds more salient, people could really focus their attention on the areas of biggest concern, whereas a rainbow color scale is basically a terrible way to visualize data in almost all cases. And just basically creates false categorical clusters, like this is the blue cluster, the green cluster, the yellow cluster, that might have no bearing on the underlying data distribution and distract.
Right.
So on that note, I should actually also give kudos to the larger Python community for the development, for example, of varieties and related color schemes that actually borrowed from color science to build things that may have their own issues, but are certainly much, much more effective than like default rainbow schemes.
Yeah, interesting. So yeah, the fact that you could, it goes back to what you were talking about before of what, and the chart you showed of what which aspects of the visualization the human perception picks up depending on the task. Yeah, cool. So what was the question? Oh, I lost that one. So to the, I'm trying to remember what, we had one more question. Oh, wait.
Maybe one more, and then so the next group can set up too.
Yeah, if people have to leave for their other sessions, please do. We're just keeping the live stream going here for a few more minutes. Here. So which heuristics and algorithms are most useful for generating suggestions in Wrangler? Is a question.
Oh, I don't have time to answer all. It's a mix of things. The short version is we handcrafted a number of rules that basically came through a lot of trial and error as a starting point. And then all of them have like weights associated with them that as we observe usage over time, we're actually relearning the weights and a number of different features to create more effective rankings over time. Yeah.
Cool.
All right. Thank you all very much.
Yeah.